All right, so welcome to Comparative Origins, and we are going to open up the curtain on this class. Pretty fancy stuff right there. So we're going to be going on a journey in this course from the beginning of the semester to the end, and that journey is going to include the structure of the naturalistic worldview. So what I mean by the naturalistic worldview is the idea that there is no God, no creator. And we are going to examine that worldview and see if it matches up with the evidence and see if whether or not the Bible is a better explanation for what we see in the world. And we're going to take that one step at a time. We begin with cosmology, which is the study of the history of the universe. So this is the section where we're going to be talking a lot about the Big Bang. Then we go to the origin of life. Can life spring from non-life? Then we talk about genetics and DNA. Is it possible that the genetic code could have programmed itself to the extent that we see it in all living creatures today? Then we look at natural selection. Is it possible that that process could have given us the diversity of life that we see in the animal kingdom? From there, we take a look at the fossil record and the geologic record, the history of these things, with physical evidence that we can actually look at in the present. And we kind of finish up by talking about radiometric dating. Were these years of 4.5 billion years for the how long the Earth's been in existence and the 14 billion years since the Big Bang? Where do all these numbers come from? And we'll examine that at that time. We end with ethics and morality, because based on whether or not we got here as a result of chaos, as a result of forces that don't require a creator or a God, that will mean one thing in terms of what we think about ethics and morality. But if we are the ultimate result of a loving God who made us exactly the way he wants us, that's going to say something completely different with respect to ethics and morality. So, without further ado, we are going to start with cosmology, and we're going to change the background right here. Go ahead and title your notes for today, Cosmology. Again, cosmology, the history of the universe, is what we're going to be examining today. And sometimes in these presentations you'll see some quotes, and these quotes sometimes won't be attributed to anybody. In this section, if they are not attributed to an individual person, that means they come from this guy, Dr. John Harnett, PhD in physics, University of Western Australia. He's done a lot of work in terms of astronomy and astrophysical research. So, first thing we want to take a look at here is a little bit of a history as to what people have thought about the universe. Go ahead and write this down, please. Just as a note, if we end up going too quick and you can't finish all the writing, these PowerPoints are on Schoology, so you can always check that too. Or if you walk in late and you miss something, you're welcome to do that. If you're the type of person that doesn't like quietness, you will not enjoy note-taking sessions. You'll notice that I was not talking about a lot of things while you were writing this down. The reason for that is because when I was in college, sometimes what professors would do is they'd have the chalkboard back then full of notes, and we were supposed to write all those notes down, and while we were writing those notes down, they would be lecturing on them. Well, at least me, maybe you guys can do this, but I can't focus on more than one thing at a time, at least really well. So when I have students write down notes, especially in this class or in astronomy, while you're taking notes, I'm not going to say anything because I know you're focused on this. So if you don't like that awkward silence, I apologize, but it's going to be there, whether you like it or not. So before 1929, the scientific community thought that the universe was not moving. It was static. It was holding still, and it had been doing that ever since the beginning of eternity, that it had been around forever. But in 1929, this guy, Edwin Hubble, he used a very sophisticated method to see that all of the galaxies that we looked at were actually moving away from us. And the way he did that was by using something known as redshifted spectra. We talk about this a little bit in physics, where we talk about the Doppler effect. Things that are moving away from us when they make noises, they sound a lot lower in pitch, lower in frequency, than if they're coming towards us. And that same thing happens with light rays. If something's moving away from us, it's shifted towards the red or the long wavelength end of the spectrum. And so because a lot of these galaxies are shifted that way, we can kind of safely assume that they're moving away from us. So this is where the idea of the Big Bang came from. It's not from some sophisticated, crazy, smart theory. It's simply by looking out in space. Everything we see, all the galaxies that exist beyond our own galaxy, the Milky Way, they're moving away from us. So then the idea is if they're moving away from us, then we can rewind the clock, so to speak, to the point where all those galaxies were in the same location. And that point in time, based on the velocities that we see, you can go back, would be about 14 billion years ago, where everything was in that one location. And so people say then that there was this massive explosion where everything just kind of shot off in every direction, and that happened 14 billion years ago. That's really as sophisticated as that idea is, just by seeing how everything's moving apart. So the question kind of becomes, why not just do that? What's wrong with looking out in space, seeing these things moving away from each other, and just saying, well, let's just rewind the clock? Why can't we just do that? Any ideas on why that might not be a good idea?
I don't know exactly what it would look like because
That's true. You can't rewind time. And that's an excellent point. When you're looking at what's going on right now in the present, you're looking at a sliver of that supposed 14 billion year history. You can't just look at what's going. We've been accurately observing these galaxies for about 30 years through the Hubble telescope, and now the James Webb telescope. You can't take a 30-year period of history and examine it really, really close and say that you can predict what happened 14 billion years ago. It just doesn't work like that. It's like, if you're playing basketball and you're watching, or maybe you're watching a game, and you observe the first minute of the third quarter, okay? and you watch that minute, you have all this sophisticated equipment and statistical analysis, and you're going to try and predict from that single minute the score at the end of the game. You can't do that because you're only looking at that tiny portion of history. Everything else is an assumption. And I'll tell you, the universe is a lot more chaotic than a basketball game. So the reason why we can't do this is because there were no eyewitnesses and you're making massive assumptions. Go ahead and write this down as well. And I gave you the basketball analogy. It is very arrogant to say that by analyzing this tiny bit of history that we can say exactly what was going on 14 billion years ago, let alone 1 million years ago or even less than that. You can't do that. Not without an eyewitness. You're making massive, massive, massive assumptions. And that's the problem with rewinding the clock based on what we see here. And this is just kind of a description on how redshifted spectra work. We talked about that briefly before. We don't need to go into it. So it's kind of interesting, though, because before 1929, everybody thought that the universe has been around, and I'll let you know what to write down. You don't need to write this down. I'll tell you exactly what you need to write down when those times come. Before 1929, everybody thought that the universe, scientists believed the universe had been around eternally, forever. It wasn't moving. So it's sort of interesting that now that people see that things are moving apart from each other, now that the science is coming in, it's pointing to the fact that the universe actually had a beginning. So one way or another, when the evidence comes in, the scientific community does at least get closer to reality, the reality that I believe anyway, that the universe was created at a certain point in time. It has not been around eternally forever. God made it, according to the Bible, about 6,000 years ago. So they are kicking and screaming, getting closer to the truth, because now they at least believe there was a beginning of the universe in their minds when the Big Bang happened. All right, thermodynamics. Who would have guessed that in a theology class, how many of you are taking this for a theology credit? Wow, that's a good amount. So who would have guessed that in a theology class you'd be talking about thermodynamics? Probably nobody. But a little bit about thermodynamics. Thermo means heat, and dynamics means how it works. So the study of how heat works. Albert Einstein once said, "The laws of thermodynamics are the only physical theories of universal content which I am convinced will never be overthrown within the framework of its basic concepts." And MIT professor Seth Lloyd said, "Nothing in life is certain except death, taxes, and the second law of thermodynamics." So hopefully you're kind of getting an idea that these laws of thermodynamics are very well established. Notice they're not theories. They are laws. There's a very big difference between the two. So these thermodynamic laws are laws which really underpin the entire universe in which we live and the world in which we live. They're very important. Nothing has ever been observed to be going against the laws of thermodynamics. First law of thermodynamics says the energy in the universe is constant and can't be created or destroyed. Pretty straightforward stuff. The main law of thermodynamics that we're going to be talking about today in relation to cosmology is the second law of thermodynamics. Go ahead and write this down, please. So we're going to kind of flesh this out over the next couple slides. But the second law of thermodynamics says all systems of matter and energy continually strive to reach the most probable state. And disorder is way, way more probable than order. And we're going to see exactly what that means in the coming slides here. There are several different ways to write the second law of thermodynamics. This is one of them. You'll see some of the others shortly. So one way you can kind of think of the second law of thermodynamics and things being the more probable state is by thinking of tossing bricks, okay? So pretend you're this blue person right there. You're throwing some bricks to the left, you're throwing some bricks to the right. Which of these two scenarios is more probable? A pile of bricks. You're not randomly going to throw bricks in one direction and have them organize themselves neatly into stacks like that. The more probable state is a disorderly one, and that's what you just wrote down means. Another way of describing it is that if you're going to go from disorder to order, you have to perform work on that thing in order for that to occur. You need to expend energy to make this orderly. Orderliness is not something that happens just out of nowhere. It doesn't happen naturally. You have to work on something. You have to do something to create that order. When you have a messy room, you can't just throw an explosion in there and think it's going to organize itself for you. You have to actually do that carefully yourself. Order does not come from disorder. Another way, so capital letter S, for whatever reason, they use that letter to describe a measure of disorder. And another way you can say disorder is entropy. So this is another example. You start with an orderly cube here, and it's an ice cube. If you put it in a temperature that it is above freezing, it is going to melt into a disorderly puddle of water. Now, it doesn't matter what you do with the temperature, this puddle of water will never reorganize itself into an orderly cube like that. You have to perform work on it. You have to do something to it. You have to scrape that puddle into the ice cube tray and throw it back in the freezer. So this happens naturally, going from order to disorder. What never happens naturally on its own is going from disorder back into order. Go ahead and write down the first bullet point and these two sub-points, please. Again, you're stopping right here. These are just two other ways of writing the second law of thermodynamics. You don't need to write those down. So to just kind of summarize this again, over time, the entropy or the disorder of the universe cannot decrease. The universe cannot, by itself, get more and more organized and orderly. That's not something we have ever observed in nature occurring. You always need something or someone to make that organization happen. So where does this come in? Well, when we think about the Big Bang, it supposedly was just this massive explosion. And out of that massive explosion, you have everything in our universe. And over time, everything in our universe organized itself into happy little planets and happy little galaxies and happy little stars. It goes completely against the second law of thermodynamics. And nothing has ever been observed to go against that law. So why is it that in the scientific community we believe that this chaotic Big Bang explosion can give you a massively organized universe? The answer to that question is beyond me. But, I mean, when you think of an explosion, it's not the sort of thing that's ever going to give you something that is organized. Imagine, so you're going to end up with a big gas and dust cloud if you do have this massive explosion. And somehow out of that massive gas and dust cloud, that organization would have to arise. You'd have to get these little planets forming, these little stars forming, and within those planets and stars and outside of them, they'd be gathered together in bigger galaxies. So let's just think about this for a moment. Let's just say that I open up my drawer here and I take out a pack of cigarettes and I pass them all out and we all start smoking. Aside from me getting fired, what's going to happen inside this classroom? It's going to get smoky. Yeah. So this room is just going to get smoke all over the place. Will that smoke gather in an organized way in a sphere in that corner of the room? No. Will it gather in the shape of a rhombus right here? No. Will it look like a triangle above the sink? No. We know just intuitively from living in this real world that smoke, gas, dust does not organize itself. It spreads out evenly. It's one of the gas laws from the PV equals nRT equation, if you're familiar with that from a class. But gas and dust never organize themselves together into organized shapes. And so just a common sense understanding of what you'd see from a result of an explosion like that, you would not expect to see an organized universe. Certainly not the one that we live in, that could have organized planets and eventually, single-celled organisms turning into more complicated ones. That's a story for later. But these laws of thermodynamics, I can't emphasize enough, they are laws. They are not theories. And for whatever reason, the scientific community puts a lot more stock in the theory of the Big Bang as opposed to the second law of thermodynamics. This is how a textbook written in 1971 finished up that talked about thermodynamics. The authors see the second law of thermodynamics as man's description of the prior and continuing work of a creator who also holds the answer to the future destiny of man and the universe. That is not the way you'd find a textbook ending these days. Because, I mean, if you just look at the evidence honestly, you know that because of the second law of thermodynamics, there's no way you can get the organized universe that we see without a creator. You always need something there to make that stuff organized and make it look the way it does. If you see organization there, it always points to a creator. And these secular authors of this secular textbook, which was in secular universities for a long, long time, there wasn't as much, political correctness back then, and they were able to say what they believed. And they believed that because of common sense. Again, when we look at this evidence, it points in one direction. It doesn't point towards a violation of the second law of thermodynamics. We don't see that anywhere in nature, so we shouldn't assume it was violated in the past. What we see indicates the work of a creator that made things in an organized way. And the Bible tells us about the organized way in which God did this. But of course, if we look out in the universe and everything looks really old, if everything looks billions of years old, then we'd have to kind of reconsider this. So, and we talk about these things a lot more when if you had ever take astronomy. So when we look out in the universe, in our solar system, in space, do things look millions and billions of years old? Or do they look more in line with biblical history of thousands of years old? And I'll just go through a couple of these with you. And this is kind of how we'll finish our first day of notes. So, on Earth, life supposedly began evolving 4.5 billion years ago. That's when the first simple cells supposedly appeared. Well, if you go by that timeline, 4.5 billion years ago, the sun would have been much dimmer because stars would go through a life cycle just like anything else. Well, if the sun was 25% dimmer, the Earth would just be a frozen ice ball. There's no way life can evolve on a frozen world. So it doesn't match up, and they call that the faint young sun paradox in the secular world. Planet Venus is one of the neat planets to talk about. It's the second planet from the sun, but it's actually hotter than the closest planet to the sun. And the way that our solar system would have formed through the Big Bang model is something known as the nebular hypothesis. So the idea is you've got this swirling cloud of gas and dust, and as that cloud is swirling, you get balls of material that begin to gather together in one location, in the middle, and that's where the sun would be. And in other locations beyond that, they'd start to gather together, and that's where you would see other planets starting to form. But the main thing is here, this gas cloud would have been swirling in a certain direction. So as the sun and the planets form, they should all be turning in the same direction that dust cloud was originally spinning. Venus is spinning the wrong way. That can't happen if the nebular hypothesis is true. Go ahead and write this one down. No. No, I'll tell you exactly what you need to write from these. If I don't say anything, just assume that it's up there to look pretty. So the Earth has a magnetic field, and it's a good thing too, because if it didn't have it, we'd all be dead. The sun gives off radiation. We call it the solar wind. The name solar wind is kind of a misnomer. It's not a warm breeze like the name suggests. It's actually giving off lots and lots of deadly radiation. And our magnetic field deflects that radiation around us for the most part. Without our magnetic field, we'd be pelted by this radiation and nothing would be able to survive. We all know that radiation makes very bad things happen. So if that's happening consistently on Earth, there's no way life could evolve, much less survive. So our magnetic field, using measurements that we see today in the present, as time goes on, it's getting weaker. It is not stable. It's decreasing over time. So there's no way that our magnetic field could have been around billions of years ago at the rate we see it decaying today. There's no way that could be. And if we didn't have a magnetic field back then, there's no way life could have evolved back then. A decaying magnetic field points to a much younger Earth. Go ahead and write this one down too. So comets orbit the sun just like planets do, but planets orbit the sun mostly in a nice circle. Comets orbit kind of like this. They get really, really close, and then they go really, really far away. Now, the closer they get, this should be the sun. The closer they get to the sun, the faster they go. And the faster they go, the more material they lose on each pass. Well, there's no way these comets could have been around for millions or billions of years because they lose too much material each time they go by the sun. And yet, here they are. The last big comet that I'm aware of was in 1997. It was Comet Hale-Bopp. I was fortunate enough to be able to see it. They stay in the sky for a long period of time because even though they move very quickly by the sun, they're still far enough away that they don't move too far in the sky over the period of each night. So you could see it for probably about half the year in the sky at different locations. It was really cool. So hopefully we get another good comet one of these years. So Mars has 2 moons, and if Mars and these moons are billions of years old, their orbit does not make sense, to the point where some in the scientific community believe that they were placed there by ancient Martians. I don't need to say any more about that. Jupiter contains gases that could not have formed at Jupiter's location. So these gases right here could only form further out from where Jupiter is located. They would not be stable at the location we find Jupiter in. And yet, those gases are right there. It doesn't add up if Jupiter was made over that 4.5 billion year period of time. Go ahead and write this one down. I think I got 2 more that I want you to write down after this. How many of you have dressers in your room? Okay. Let's say you keep your dresser nice and organized, there's nothing sitting on top of it. What happens if you don't clean your dresser over a period of a couple months? It gets real dusty. It gets real dusty real fast. Same thing is true in space. So these rings of Saturn ought to be very dusty. There are micrometeorites out there is space dust out there. These rings and the ice and the rocks that make them up should be quite dirty, just like your dresser would be if you left it for a long period of time. If these rings are 4.5 billion years old, they ought to show the dirtiness of 4.5 billion years, but they don't. They are in absolutely pristine condition. They do not look that age. Write this one down too, please. So Triton is a moon of Neptune, and it has cryogeysers and cryovolcanoes, which are kind of like the volcanoes and geysers we have on Earth, but instead of the volcanoes shooting up lava, it shoots up water and other volatile materials. Now, if Triton was 4.5 billion years old, all of this material should have long since been gone. If it's been erupting for that period of time, it would have run out of material by now, quite simply. And lastly is Pluto here, and I'll put this up at the beginning of class tomorrow. You can write this one down too. But Pluto is this small world deep in our solar system, and it was expected to just be a cold, dead, uninteresting place. But predictably, when we got there and took pictures and made measurements, it was the exact opposite. It is a very young-looking world, and we'll start talking about Pluto when we come back tomorrow. See you then!
Yeah, you almost an actor.